Welcome back. Today I will define the complex analysis. We all of us know in real analysis, function defined from real line to real line. And in complex analysis, all the function defined as w equal to fz, where z equal to x plus iy, and here the function is defined by complex number to complex number. Here the variable z is called complex variable. The set S is called domain of the definition of fz, and the set of complex number who is actually w equal to fz. Here assume as z varies on the set S, which is called the range value of the function fz, and let u and v be the real and imaginary part of w. Then if z equal to x plus iy, then it map w equal to fz, where fz equal to uxy plus ivxy. That means a complex function fz here is equivalent to two real value function uxy and vxy, each depending on two real variable x and y. Here we would use the fundamental theorem of intermediate value theorem, Taylor's theorem, fundamental theorem of calculus, mean value theorem. So we are taught in the course of real analysis. Here also would be used the line integral, the concept of Green's theorem, surface integral, which we are taught about the first course of multivariable calculus. Actually today's topic is, today I will discuss some basic concept about complex analysis. I will say actually some topology on this analysis. Then in my next video I will deeply discuss what is the analytic function. I will deeply discuss the complex analysis in my next video. Today's part is actually basic part. At first you have to learn the analytic function. What is the analytic function in complex analysis? For this you have to learn the power series and Taylor series, and we have defined in my previous lecture what is the power series, what is the radius of convergence, interval of convergence. At first I will highly recommend you, if you don't see my previous video, at first see this video, then today's video would be slow. Clear? Okay. Now I will discuss some basic part actually which depends on topology. I will discuss some basic part. I will say one mapping by exponential function. How do we like the mapping in the complex plane? Fz equal to here w, and w equal to exponential function means e to the power z, and obviously e to the power z means e to the power x plus iy, which we can write e to the power x times e to the power iy. Now consider rho equal to e to the power x and phi equal to y. Then this reduces w equal to rho e to the power phi. Then the transformation would be, how look like the picture? First fix x equal to c1. X equal to c1 means this vertical line. Then when x equal to c1, then w equal to e to the power c1 times e to the power iy. And consider e to the power c1 equal to rho 1 e to the power iy. Then the picture would be, here rho 1 means rho 1 e to the power iy. That means this would be look like circle of radius rho 1, and since here y equal to 0, that means angle of the circle would be 0. That means circle would be such type, and when the point varies in this way, then this would be such type. That means this is the rho 1 e to the power iy is a circle. That means this vertical line map to this circle. I hope my all viewers have understood the picture. Okay. Next, the vertical line map to circle, and when 2 pi, then the point of the circle would be belongs to go back here, and when x equal to 0, that means this y axis, then the picture would be, then since e to the power x equal to 0, that means w equal to e to the power iy. So this is actually the circle of radius 1. That means when x equal to 0, that means y only y axis, then this map circle of radius 1. When x less than 0, then this map the circle inside the circle of radius 1. This type of circle always lies inside the circle of radius 1. For all vertical line, always I will get different type of circle, and when x goes to infinity, then it cover. This would be such type of circle. Okay. That means circle would be such type. And when x goes to infinity, then it covered the whole complex plane. Always it would be circle. That means all vertical line always map to circle. Okay. I will see some subset of complex number BAR. We all of us know BAR in metric space. What is the BAR? In complex plane, BAR means Z in complex number. Here Z be the member of complex number such that absolute value of Z minus A less than R. That means this is, we all of us know, this is the ball of radius R centered at A, and for example B of I comma 1. That means here center is I, radius 1 ball. This is Z in complex number such that absolute value of Z minus I less than 1, and the picture is such type. Here the point is I, here the ball of radius 1. That means this type of ball This is denoted as B of I comma 1 and this ball is open. Okay. Here also use this term mod z term. Mod z term means we all of us know this is the distance between 0 and z in the complex plane. And mod z1 minus z2 means distance between the complex number z1 and z2 in the complex plane. And BAR closure means set of those complex numbers such that mod j minus a less than equal to r. This is actually closed ball of radius r around the point A and BAR closure minus BAR is the set of those complex number such that only the mod z minus a equal to r. This is the BR closure minus BR. We all of us know this part. Today's topic is just as a review because this part would be helpful to understand the complex analysis, every theorem, every exercise in better way. Next I will see what is the upper half plane in complex plane. Upper half plane. This is denoted as pi. Pi is set in complex number such that imaginary z get strictly greater than 0 and notation is such type. This is the upper half plane. And if imaginary z less than 0, then this would be lower half plane. We will see what is the annulus. Annulus means set of those complex number such that R1 less than mod z minus a less than R2 means the picture would be such type. This is the ball of radius R1 and this is the ball of radius R2. And here notice R1 strictly less than z minus a strictly less than R2. That means this region be the member of annulus. Such region is called annulus. I hope my all viewers have understood. Here this is the inner circle and this is the outer circle. And this middle point is belongs to annulus. We all of us know actually what is the open set. Now I will say what is the open set in complex plane similar to real line. A set A which is subset of complex number is open if given z belongs to A. There exists ball of radius r greater than 0 such that this ball always contain on this subset A depending on z. This is actually definition of open set we all of us know. Some example of open set: ball of radius r with center A is an open set. And ball of radius r with center A is, we all of us know. Z belongs to C such that mod J minus A less than R. Empty set is an always open set, and we all of us know if S1 and S2 be two open set, then their intersection always be open set. Take arbitrary collection of open set, then their union is always open. This is the idea of open set, and idea of closed set is a set F is closed if their complement is open, means C minus F is an open set in complex number. We all of us know, similar to real number, similar to metric space, the idea of open set and all idea of basic topology is same. Review, I have introduced this. Now BAR closer, obviously this is closed set because C minus B are closer equal to Z belongs to C such that modulus of Z minus A strictly greater than R. Obviously this is an open set. So B AR closer is a closed set. I hope my all viewers have understood this. What is the closed set? Another idea of closed set, a set F is closed if every point is a limit point. Now I will say what is the definition of limit point in complex analysis. Similar to real number, point Z in the complex number is called limit point of a set S if W belongs to C such that 0 greater than W, absolute value of W minus Z less than R, intersection S not equal to 5, and this is true for every R greater than 0. That means a point Z is a limit. If a point Z is a limit point, then after some stage, every ball around this point Z for any radius would be intersect the set S, and a point of S which is not limit point is called isolated point of S. For example, any point with the circle of radius 1 mod Z equal to 1 is a limit point of the set Z in C such that mod Z less than 1. That means the ball of radius 1, if we consider this interior of the set, then you can get any point in this interior of this circle which is arbitrarily close to this point. So any point which lie on the boundary always be limit point of the set, which those point which lies is the interior of this circle. I hope my all viewers have understood. Just say, pick any point, and if you consider any ball of radius, some radius around this point, this ball always intersect this set. Okay. Now I will see one nice example. I will see the set S which contain the element look like x plus iy, where x and y belongs to rational number. I will say every complex number be the limit point of this set. We all of us know all the point with rational quadrate always tends in the complex number. This at first consider z equal to x plus iy be the arbitrary point in the complex number. Consider z equal to x plus iy. Now consider one ball of radius epsilon. Then the point which touches the horizontal axis, this would be x plus epsilon plus iy, and the point which touches the vertical line, this would be x plus y, I plus times y plus epsilon, and the coordinate of a point of 45-degree angle to the horizontal on the boundary would be x plus epsilon over square root of 2 plus I times y plus epsilon over square root of 2. Take this epsilon ball, then take this square. Always this square contain this epsilon ball. Therefore, b prime z epsilon intersection s would be always not equal to phi. That means this ball always intersect the set S, where the set S is x plus iy, where xy belongs to rational number. And this is true for all complex number. And this property actually true because we all of us know all the point with rational coordinate always dense in complex number. So all the point with the limit point of the set S. I hope my all viewers have understood. Just see the picture. If you see the picture, then you can understand in better way. Okay? Well. And similar to real number, similar to real analysis, continuity in complex analysis, always I will define by sequentially. A function f which is defined from complex number to complex number is continuous if for all sequence Zn in complex number such that Zn as n goes to infinity, Zn goes to Z0 imply f of Zn as n goes to infinity, f of Zn goes to f of Z0. And we all of us know in real analysis differentiability is a local property similar to in complex analysis differentiability is a local property. Differentiability always at the point Z0. Obviously, this Z0 be any arbitrary point in complex plane. Actually, all complex analysis depend on differentiability. So, just recall what is in complex analysis differentiable at a point means. Consider a subset U which is contained in the complex number and Z0 be arbitrary point in U. Now consider f from U to C is complex differentiable at the point Z0 because I have said differentiability is a local property. If limit z goes to Z0, fz minus fz0 over z minus z0 exists. Sequentially, for all sequence Zn which contain U omitted Z0 with the condition Zn goes to Z0 as n tends to infinity, then the sequence fzn minus fz0 over Zn minus Z0 converges to the same limit, then we can tell the function f is differentiable at the point Z0. This is the idea of differentiability. In my next video, I will discuss this part elaborately, because in my next video, I will discuss what is the analytic function in complex analysis. Okay? See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.